So let's talk about now divergence. And divergence is a really key idea inside of physics, inside of electromagnetism. It ends up becoming something that really, also when we work in dynamics, that sort of thing. So it ends up becoming very handy or powerful for people who are in engineering, who are inside of physics, or are doing more applied mathematics. So what the concept of divergence is that it's essentially an operation that tells us how a field behaves towards or away from a point. So a way to imagine this is to imagine a fluid vector field, F. And so F is the velocity of the fluid. So what div F is the net rate of change with respect to the time of the amount flowing away from or to the point P. So what you want to imagine is that you've got all your vectors. You select a point P inside of the vector field, and you can imagine your vectors. Some things are going to be flowing towards that point, and then other vectors are going to be moving away from it. Okay, and so if we've got more, if we add up all those vectors, or all those the magnitudes of those vectors, and we subtract the ones that are moving away, okay, we end up kind of understanding what the divergence is of this of the vector field at that particular point. So some general rules that we want to think about when we talk about divergence is the positive divergence is going to be the flow away from the point is greater than the flow towards the point. So if we have more flow away from the point than we have going towards the point, we're going to have positive divergence. Negative divergence is when the flow towards the point is greater than the flow away from the point. So the flow going towards the point, right? We've got bigger vectors going towards the point than going away from the point, and so consequently we end up with negative divergence. And then we have zero divergence, and that's when the flow towards the point is equal to the flow away from the point. So what we're going to do is we're going to take a look at a couple of examples here, and what we'll see is we'll develop kind of a method for determining basically what the divergence is based upon looking at the vector field. So let's take a look at some vector fields and see if we can figure out what the divergence is for these vector fields. The technique that we're going to use is essentially we're going to draw a circle, a small circle, in an area or region of the vector field, so that they'll help us to determine in that basic area or region whether or not we have positive divergence, negative divergence, or zero divergence. So let's imagine that I draw, so there's my circle here. I'm going to draw that circle there. And what you want to see here is you want to see that all of these vectors, they're all the same size. And so I've got these vectors here, they're all flowing out, away from this particular region or area, and these are flowing in. And they're all the same size. They're all the same size going in, also in the same direction. And so what you can tell here is that the amount of flow in is equal to the amount of flow out. All right. So on visual inspection, we can say that the div of this F here is equal to 0. Okay. If I select a different area, so let's say, for example, I go down here and I select this area down here, the question is whether or not this is in fact true down there as well. Okay. So for this area, we got the div of F is equal to 0. Well, if you look, all of those vectors, they're all the same. Okay. They are basically all the same size. Okay. And they're all kind of pointing in the same direction. And so consequently, the amount of flow in that area is also equal to the amount of flow out. All right. And so the divergence here, div of F, is also equal to 0. 0, not the 0 vector, but 0. And so what we get here is, or we can understand this as anywhere inside of this particular vector field, we're going to have the same occurrence happen. And you can draw circles around anywhere in here, and you'll see that the vectors in are going to equal the vectors out. So for the entirety of this vector field, we have the div of F is equal to 0. Okay? Div of F ends up equaling 0. Now let's look at this vector field. When I look at this vector field, let's say, for example, I select this point right here. Okay? Select, or that region right there. And when I select that region, what you want to notice is notice that the vectors moving into that region are bigger than the vectors that are moving out of it. Okay? They're larger than the vectors moving out of it. Not only that, we can also see that there's some slight changes in terms of the direction. We've just got more flow in, right? More flow in than out. Okay? And so if you remember, when we go back up, we'll go back up to our statement, the flow towards the point is greater than the flow away from the point. That's when we have negative divergence. And so you can see, at least in that area, we're going to have negative divergence in that area. Let's take a look at another region. Let's say, for example, we come in here around the origin. Well, if we look at around the origin, we pretty much have the same thing. Okay? You can see that these vectors, they're larger outside of the origin. Okay? And actually everything around that origin is moving in towards, we don't really have anything moving away from the origin. It's all moving in towards the origin. And so, as well, we can see there that we're going to have negative divergence. And in fact, for this particular vector field, we have negative divergence all the way through. You can actually see it. We could select a region down there, more going in than coming out. Okay, and so consequently, that's one of the ways that we can actually analyze that we have negative divergence happening here, or we can see basically we don't get an exact number here, but we can basically see what the divergence is coming through. Let's take a look at this one. Now this one's a bit more complicated. Let's say I come in here and I'm going to select, we'll pick this region right here, okay? Pick that region. And if we look, all right, I've got smaller vectors coming in than I have coming out, all right? So there's more flowing away from than flowing in towards this particular vector field, this particular region. So what I have here is I have positive divergence in that region. But if I come over here now and I look over on this section over here, you can actually see the opposite happening. Over here, okay, I have bigger vectors flowing into the region and smaller vectors flowing out. And so in this region over here, I actually have negative divergence. So for this vector field, what I have is I have a variable divergence. Okay? So what we want to look at here is we want to remember those basic rules for whether or not we have positive or negative divergence. Okay? We want to remember that if more is flowing out than flowing in, it's positive. If more is flowing in than flowing out, it's negative. And if they're balanced, we have 0. Okay? And basically what that is it's looking at the size of the vectors in the vector field, okay, and kind of thinking about if I added up all of them, which ones are going to be bigger, right? Which are going to have the bigger overall total. All right, is it the outward ones or the inward ones? And that pretty much tells me what my divergence is from our visual inspection perspective. So now we want a mathematical definition for finding our divergence. So if F is our vector field and it's PQR in R3 and PX, QY, and RZ all exist, then the divergence of F is defined by div of F is PX plus QY plus RZ, which is basically the partial of P with respect to X plus the partial of Q with respect to Y plus the partial of R with respect to Z. Okay? And you can see here that we're going to get, this is why we talk about like the net flow, right? This addition here, that is a net. You can see the net there, okay? And since we're taking the derivative of these vectors, what we're getting is we're essentially getting kind of like we're adding up all of the movement in and subtracting out, or excuse me, we're adding up all the movement out and subtracting out all the movement in, okay, to give us our value here. Now, you want to notice here a couple of things about div f, right? So div f is a scalar, okay? It's a scalar, and what that means is that means it either gives me a function or a scalar value. Now, when we actually analyze it or we evaluate it at a particular point, it's going to give us a scalar. It'll give us the actual divergence at that particular point, and we'll see that that's the case, all right? If, on the other hand, we just want to know in general the divergence of the vector field, that's when we're going to get our function, right? So this is of the field, and this is of at a point. Sometimes you'll see that what we get is we actually get a scalar value for the entirety of the field. And that does happen. Whatever it is, you want to understand that div f is not a vector. So div f is not a vector, okay? Instead, it is a scalar value, right? And it tells us something in terms of like the overall total or quantity, and it's that quantity of flow. So let's now go in and calculate the divergence. And we'll have f of xyz equal xy, 5 minus z squared y, and x squared plus y squared. And we'll do that at 0 to negative 1. So what I'm going to do is I'm actually going to go in and I'm going to find div of f, that function. So we'll start out with that function. And so it's going to be the partial with respect to x of xy. So that'll be y, plus the partial with respect to y of q. So here's our p, here's our q. So that's going to end up being negative z squared. And then the partial of r with respect to z, and so that's plus 0. Because there's no z's in there. So it's going to end up being y minus z squared. Now what I'm going to do is I'm just going to plug in my point. So I've got 2 minus negative 1 squared. So this is going to be equal to, so div of f at 0 to negative 1 will end up equaling 2 minus negative 1 squared, which equals 2 minus 1, which equals 1. Okay? Couple things to notice here. Notice that the divergence for f for this vector field is actually variable. It depends upon where we're actually going to find where we're finding our divergence, and that'll tell us what it is at each and every point. It's not the same for every piece. Okay? But once we actually select a point, we can go out and we can find that value just by plugging it into the divergence equation. Now let's find the divergence for, say, something like this, f equals negative yx, which ends up being this radial vector field. Now, what I want to look at here is I want to notice that if I take and I look at it and I consider my divergence instead of a particular area, you can actually see, right, the amount that goes in and the amount that goes out are actually pretty much exactly the same, right? You can, anywhere you want to look, if you want to go and take a look around the origin, the amount going in, the amount coming out, they're pretty much exactly the same, okay? And so our instinct here is that the divergence of the entirety of this vector field is going to equal 0. So we want to see, is that actually the case? Will we actually get the divergence equal to 0? So we're going to find the divergence for f. Here's going to be our p, here's going to be our q. And since we're in 2 dimensions, we only need to find px and qy. Okay? So what we can see here is that div of f is going to end up equaling, well, the derivative with respect to x of y is 0, and the derivative of x with respect to y is 0, so 0 plus 0, and that ends up equaling 0. So for this particular vector field, you can actually see that for the entirety of the field, okay, the divergence is actually equal to 0. And this is going to actually become very important for us as we talk about things like what's called a source-free vector field, right? Whether or not we actually can find a stream function. That is that we can use our fundamental theorem of line integrals for flex in this case. And so consequently what you can see here is that in some cases our vector field doesn't necessarily have to be constant, right, for us to actually have a zero divergence.